Before we get to 100% formal, I would like to do one more intuitive sketch just to help you understand what we're going to do ultimately. Okay, we're still going to use a sequence, so it's not exactly informal. It's more like a semi-formal in this particular part of the lecture. All right, let's talk about it. How can we sketch the proof obligation or verification condition rule of invariant preservation? How do we do that? So this will be the sequence that we have to eventually make it formal. So at the moment, you can see turnstile, that's a sequence that we just spoke about earlier, is definitely a formal concept. However, the hypothesis over here and also the goal over here, they are not exactly formal. I'm still using the natural language to specify them, but that's okay. I think let's do very slowly, because eventually we'll get to something extremely formal, 100% formal, but I'm concerned that you might just easily get lost if I show you the math directly. So I would suggest we have some this intermediate buffering slide just to make sure you understand the conceptual idea first before we get to be purely formal. Okay, let's do it. And this will be I'm going to talk about the rule over here. Let me just go directly to the annotation over here. Right. And just for your information over here, I'm including also the model M0 over here, right? This is our model M0, because don't lose the big picture. The reason that we want to do invariant preservation proof obligation is because we want to somehow justify our model M0 is actually correct. That's why we're doing this, right? We are not really coming out of this proof obligation out of nowhere. That's not what we're doing. Okay, and this part here is about the so-called proof obligation rule. Okay, so let me just mention terminology over here. This entire thing here is called a proof obligation rule. Proof obligation or verification condition rule for invariant preservation. Invariant maintenance or preservation. Right, so there's a rule over here, and the rule actually got certain components that you want to really watch out for. Okay, so that will be the rule. Okay, the entire thing. And first of all, this part over here is about the invariant IMV over here. So this is the name of the rule. And later on, we're going to see other different kinds of rule. For example, deadlock freedom. So we're going to see a different name. But for now, IMV will stand for the invariant preservation. Right? That's number one. Number two, so this is the rule itself over here, which will be specified as a sequence over here. Right? You can see the turnstile that we learned about earlier. Right? You can see the turnstile over here. Right? Actually, let me use a slightly different color over here. Okay? So this will be the turnstile that we spoke about earlier. Okay? The turnstile. And we got hypothesis over here, and we also got the goal over here, right? And we are saying that we want to prove the goal. The goal should be provable, assuming that the hypotheses are actually true. That's what the meaning of a sequence is that we spoke about earlier. And I want to try to trace each of the components in the sequence over here back to the original model, just to make sure you understand exactly how things are being connected to. Okay, let's start from the axiom. Okay, for axiom, let me now simply use maybe yellow. Okay, the axiom. So the axiom over here is basically about this single axiom over here. We simply assume that D is a member of the natural number, right? That's something we can assume, something we don't need to prove. And also we talk about the next one, also the invariance. But for the invariance, now we're talking about in the pre-states, before the state transition occur. Okay, so this will be invariance satisfied at the pre-states. Okay, you can think about the pre-states that we spoke about last time is before the state transition occur. Before state transition occur. And of course, for the post-state, it will be after the state transition occur, which we'll speak about a little bit later. And what about invariance? So you can think about we are really referring to the same invariance, but the same invariant will be instantiated in two contexts. One will be instantiated in the pre-states. The other one will be instantiated in the post-state. We'll see both. Okay, But let me now just annotate the same invariance over here, but I'm going to say in the pre-states. In the pre-state, remember all the variables will be unprimed. What we spoke about, right? We talked about in the last week's lecture, the final part, we talked about how to formalize the actions for events using before-after predicate. So this is exactly where we have to use it, right? We spoke about, for example, for variable n, and whenever we talk about just n versus n prime, right? So this will be the before states or pre-states. And the n prime will be the after states or the post states. This is something I would like to remind you very quickly, right? You should really distinguish between these two notions over here. And of course, if I want to be very picky about the color of the fonts over here, they should be actually pink over here, right? But just for this part here, it can just be okay. I think that's good, right? So we talk about the pre-states, we talk about the post-states over here, or before versus after states. What's going to happen in the invariance over here in the pre-state? We simply make sure, assuming that n is a natural number, and also n is less than or equal to the upper bound for the breach island compound, right? That's what we can assume. And also, the third thing will be, we want to make sure the guards is actually satisfied for the events. And there's something I also want to emphasize, which I didn't quite mention explicitly in the slides. Okay, you can see I said the events. So there's a reason why I'm using this language over here, right? So whenever we talk about the proof obligation rule, it's only for one single event. For one single event, it's really important for you to keep this in mind. For a single events. Meaning that the same proof obligation rule should be somehow instantiated, one for ML out and one for ML in. I'll talk about specifically about systematic generation of the proof obligation rule, but at least you should know for the same invariant preservation rule, it should be applied to each of the events separately. So at the moment, I only got 2 events in my model, so that means it will be instantiated twice. But later on, if I got multiple, more than, let's say, 10 events in the system model, in that case, the same rule should be instantiated 10 times accordingly, right? Okay, so that should be for a single event. It's so important for you to know this part over here. All right, so that's why I say it will be the guards of the events. But in our case, for ML out and ML in this case, their guard is really the same because they're missing. As I said before, the guard will just be true. Right? Let me annotate just once more, just to make sure you actually remember that. Okay, so the guard over here, and also the guard over here is simply just true. So the guard is simply just true, and the guard for this one over here is also true. Right? And let me mention one theorem that I'm pretty sure you learned about before, but let me just mention that quickly. Okay, so the guards of the events, in this case, it would just be true, meaning that for each of the events, they are always enabled. In that case, there's nothing that will be so useful to add them as a hypothesis, because think about what's happening over here. Let me just put it here. If I have a sequence over here, if I say I got hypothesis 1, I got hypothesis 2, all right? And then let's say turnstile, and then one single goal. Let's say that's what I have, right? So there is one convention about the syntax which I didn't mention when I did the introduction, but let's talk about it now, since now it's relevant. If you actually got 2 separate hypotheses, right? Remember we said it can be a set. H1 is hypothesis number 1, H2 is hypothesis number 2, right? It will be as if we try to conjoin them together, meaning that you can assume this and also you can assume that, right? So what we have is over here we got H1 and H2 implies G. So this is the formal meaning of this particular sequence over here, right? It's so important for you to see that, right? So this one over here is equivalent to that, right? And what if for example, if the guards of the event, in this case for ML out, is actually true, what does it really mean? When one of them is actually true, when one of them, let's say, if H2 happen to be true, that means H2 over here is actually true. What will be the consequence of this? Well, the consequence would be, it would be as if we did not even declare H2 over here. We only got H1. Remember, there is one property for conjunction called identity of conjunction, which I also need to mention quickly here, right? Identity of conjunction, right? So that's simply, if I say P and true is equivalent to P. Intuitively, this makes sense because we're saying that if you got one of the operands for the conjunction to be true, whether or not the entire conjunction should be true still depends on P. Because if P happen to be true, good, then the result will be true for the conjunction. If P happen to be false, but too bad, the entire conjunction will be false, right? It's called identity. And also another one, which I can also mention, is called the zero of conjunction. If I say P and also false, it would be equivalent to just false, right? So you can see these rules, I didn't really mention them in the review lecture, but I think we can just mention them just in time, whenever that's relevant, right? You can see earlier we talked about the zero of implication and identity of implication. And now we talk about identity of conjunction and zero of conjunction. You might be wondering, what about the identity of disjunction, what about identity of disjunction and also zero of disjunction? It will be symmetric to what we are having over here. Since we are not talking about since we are not really using the identity of disjunction or zero of disjunction right now, I'm not going to mention that, but you can definitely look it up, maybe in your earlier notes, or just look it up, right? If we need to use it later, I'll mention that. Okay, but this will be good enough for now. All right, so if I got H1, okay, so here, what I'm trying to say is if the guard of the event is simply just true, that would be as if we didn't have this rule over here in the hypothesis, because the true over here will be absorbed by just H1 because of the identity of a conjunction over here, right? That's something I want to mention. But in general, you definitely should remember, you should always include the guards of the events. Of course, in the special case where the event guard is simply just true, like an ML in and ML out, which somehow maybe will prove that it's actually wrong. In that case, the guards of the event can just be discarded in this case. All right? That's about the guards of the events. What about the final part, which is very important to note? This part here is about the invariance of the satisfied. The invariance should be satisfied at the post states. So we're talking about the same invariance over here. The same invariance, remember the same invariance was evaluated in the pre-states. That's why I highlighted already in green. But we're going to evaluate the same set of invariant conditions the second time after the transition in the post states. But how exactly do we evaluate? So now let me show to you. You want to say here, invariant number 1, invariant number 2, they should also be evaluated. But exactly how? Let me be precise over here. The same invariant is going to be evaluated twice, let's say in the pre-states. Right? In the pre-states, what we're going to evaluate will be, first of all, we're going to say n will be the pre-state value for n, variable n. Should be a member of the natural number. And also, we want to make sure both are satisfied, so that should be a conjunction. And also n less than or equal to d, right? You can see here we got this and this. Both are using the pre-state value of the variable n, right? The two invariants. What about in the post states? In the post states over here, or the after states, what we should really remember to have is the before-after predicates, right? You want to think about what's the before-after predicates over here. And we talked about before-after predicate last time. You can definitely refer to it. In this case, we are saying that the post-state value of n should become or substituted by the pre-state evaluation of n plus 1. And also here, the post-state value for n should become the pre-state evaluation of n minus 1. Right? So let me just write down the before-after predicates. So the before after predicates over here is m prime is equal to m plus 1. And this part here is m prime equal to m plus 1. So let me now get to the post states. If I want to evaluate the same invariant in the post states, first of all, I want to make sure the post state value of n, which will be n prime, is a natural number. And also, the post state value for n, which is n prime, is less than or equal to d. But now, since we know the n prime is indeed the pre-state value plus 1, and also here it's the pre-state value plus 1. Oh, sorry, minus 1. Beg your pardon. Minus 1, right? So that means this part over here, m prime, can be replaced by m plus 1. And this part over here can be replaced by n minus 1. Essentially, we talk about the pre-states versus the post-states. To begin with, we definitely want to distinguish between n versus n prime. That's what I did in the first place. However, since we have the before-after predicates formulating the effects of the actions of the events, so we will be able to replace the n prime over here by its pre-state evaluation. In which case, we will be able to only consider the pre-state value when we do the proof. So that'll be much easier. So we don't really have to worry about dealing with n versus n prime differently. So we're just simply substituting n prime by its pre-state evaluation into n plus 1. Okay. Right, so it's really important for you to see what I'm doing here. Right, I'm just trying to review what we did last week and also to show to you exactly how the proof should really go. Right. Let's now just do one more annotation, and I believe that's everything I want to say. Right. So you want to make sure you understand this part over here, n prime, for example, over here, this part over here alone. Right, just one example. So this will be basically we are trying to substitute n prime by expressions on n according to the before after predicates, right? We're substituting n prime, which is a post state value, by expression on n, which is a before state value. And the way to really find out the relationship between the post state and also before state will be the before after predicates. Exactly, right? So that's exactly what we're doing. So that's why the BAP over here is so important to know. And don't forget, this proof obligation must be instantiated for both event ML out and also ML in, because they got different before after predicates over here. One is for n plus 1, the other one is for n minus 1. And you can see the invariance, some condition might fail, some condition might actually pass at the moment, but that's something we'll make it more precise later. All right, so that's about a very intuitive sketch to really make sure you warm up to really see the formal mathematics, like how things should be formulated precisely and also how things should be proved precisely. Let's go back. Finally, let's now review once more. Informally, what this particular sequence is really trying to say is it kind of requires us to prove the following. Whenever you got some proof obligation rule or verification condition rule, that means you have to prove that the sequence over here is a theorem. Meaning that you want to prove that this implies this formally is a theorem. Okay. Informally, well, what's really there? We say that assuming that all the axioms, the invariants, and the events guards. So we talk about one event at a time for each rule, right? So here we're saying all the axiom, all the invariants in the pre-states, and also the guards of the event evaluated true to be in the pre-state, assuming all these. After the state transition, meaning that the effects of the events will actually take place. The effects of its action will take place. In that case, will result in the post states. We want to make sure at the post states, the invariants are still satisfied. And of course, the way to really make sure everything will work is to make sure, to really specify this part over here, we have to do the substitution, like what I did over here. right? You can see here, we started with m prime over here, but we have to substitute it by the pre-state value over here according to the before-after state, before-after predicates, right? Hopefully that's clear intuitively, right? So now we will be ready to really take this informal sketch, and then we'll try to turn each components there into formal constructs.